A rectangular piece of metal measures 91 centimeters by 16 centimeters. 4 identical circular discs are punched out of this metal piece. The centers of the circular holes are on the midline of the rectangle AJ as shown. These 4 holes are equally spaced along this piece of metal. That is, AB is equal to CD, for example. A, if the radius of each hole is 2, what is the distance along the midline between adjacent holes? For example, what is the length of CD? Let's label this. So AB I'll call X, and since AB is equal to CD and so on, these are all X's. So these, I guess, spaces. And then the radius, they'd say, is 2. So that basically, well, let's just call it R for now, and then we'll fill in the R later. Like that. Okay, so the whole way is the 1, 2, 3, 4, 5, 5x. And we've got 1, 2, 3, 4, 5, 6, 7, 8 of those R's. And they all equal this 91. Okay, so now we can go in and plug in that 2. So they told me that the R is 2, so that is very helpful. And then you just solve for this, and I'm sure you're more than capable of solving that. And when you do, you get X is equal to 15. So well, they're asking, what is the length of CD? Well, CD is 15 centimeters. B, if the distance along the midline between each adjacent hole is equal to the radius of each hole, what is the radius of each hole? Okay, so basically what this means is that they're saying that X is equal to R, according to my labeling. Okay, so that's not a problem. Go back to the original equation. 5x plus 8r is 91. X is equal to R. So I just substitute that in. So 5r plus 8r is equal to 91. So 13r is 91, and therefore R is equal to 7. And part C, show why the fact that holes must be circles means that the distance between adjacent holes cannot be 5. Okay. So I guess we're right back to the same formula again, and let's see what happens. Something obviously will happen that is not possible. So they're saying this time that they're making 5 centimeters as the value for X. So this is going to be 5 times 5 plus 8R is equal to 91. And when you solve for this, you get R equal to 8.25. Okay, so you think, okay, what's wrong with that? Well, what's wrong with it is the following. If you look at this from the top to bottom, right? If R is 8.25, then that means the diameter of that circle would be twice that, which is what, 16.5? Well, that's not possible because that exceeds the entire top to bottom distance, which I believe was 16. And they've said in this question that these circles are inside. And let me just double check here. The 4 identical circular discs are punched out in this piece of metal. So obviously they cannot extend outside that, according to the question. And I think that's pretty much it. I mean, I think that's, you just kind of have to explain that 2R has to be less than 16. And in this case, this 2R is 16.5. So therefore, R could not be equal to 8.25. So you just have to explain that in words. A bump can be added to any line segment through the following process. Break the segment into 3 segments of equal length. Remove the midline segment. Add an equilateral triangle-shaped bump with each side length equal to the removed segment. The series of diagrams below shows a bump being added to a line segment of length 3, transforming it into a path of length 4. A line segment of length 21, how long will the path be after the bump is added? So let's see, this is 21. First step is breaking it up into 3 segments. Well, we're supposed to be equal, so 7, 7, 7. And then removing the middle one. So let's remove the middle one. And then finally, we got to add an equilateral triangle like that. So this is 7, this is 7, this is 7, and this is 7. And this dashed line sort of represents what was removed, and that was also 7, by the way. So now the path, this path right here, is going to be obviously 7 times 4, which is 28. Part B of this question, a path with exactly one bump has length 240. How long was the original segment? Okay, so they're sort of working backwards this time. So let's just go back to the original question. Now they're saying they have something like this, but instead of 28, it's 280. Okay, so that basically means that this whole thing is 280. So if that's the case, then each of these would be a quarter of 280, right? So what's that? 170. Oh, wait. What is it 280? 240. Sorry. 240. I think I got confused with that one. Okay, so 240. So each of these will be a quarter of 240, which I believe is 60. Okay, so that's 60, that's 60, that's 60, and that's 60. Now remember that was taken out. Now let's go backwards. Let's go to this step. That basically means that this was 60, this was 60, and then this dashed line is 60. And then let's go to that step. That means that there was 3 equal lines of 60 each. And that pretty much means that the full distance was 180. So just working backwards from question number 1. Part C, Lynn starts with a line segment that has length 36 and adds a bump to it. She then adds bumps to each line segment of that path. The resulting figure is shown below. What is the total path length of the resulting figure? Okay, so a few more steps this time. So this is 36, and it was broken up into 3 segments of 12 each, I believe, right? And then the middle segment was taken out. So this is 12, this is 12, and then that's the segment that's taken out, and then they built this equilateral triangle, so those are going to be 12 and 12. So this has a total length of 48, correct? Okay, so then what they do is they take each of these guys, like AB, and they do the exact same thing. So if you break up AB into 3 segments, it would be 4, 4, 4. So this would be 4, this would be 4, and then therefore that would be 4 and that would be 4. So A to B, that line segment this time, if you follow that path, that's going to be 16, I believe. Yeah. And then the same thing from C to B, that's going to be 16. C to, there's nothing labeled here. And then that last one is also 16. So 16, 16, 16, 16. So the total would be 16 times 4, which is 64. Okay, and finally, N starts with a line segment having length equal to some positive integer n. Then adds a bump to it, resulting in path 1. She then adds a bump to each line of segment of path 1, resulting in path 2. She then continues this process to create path 3, 4, and 5. If the length of path 5 is an integer, determine the smallest possible value of n. Okay, so we are now starting with n. There's no numbers this time, so we can work with this, not a problem. So this is a line with a length of n. So let's break it up into 3 equal segments, right? So each of those segments would be n over 3. Correct? Okay, so then we take out the middle guy, take it out, and then we build that equilateral triangle. So this is n over 3, this is n over 3, that's n over 3, and that's n over 3. So the total length of this guy would be 4 times n over 3, if I'm not mistaken. And that is the length of path 1. Path 1, if I can spell path. Path 1. Okay. So now we have to do this again and again, but instead of doing it again and again, we're going to have to find what I believe is a shortcut, meaning how do we get to this 4n over 3? Well, I'll just do one more, and hopefully it will seem like a pattern. So let's just do it one more time. I'm not going to do path 3, 4, 5, but I'm going to do path 2 at least. See, we're just looking at this guy because that is the one we have to split up. So instead of looking at the entire path, we just have to look at that one guy. That is n over 3. And then we can talk about the other ones, which will be exactly the same. Got it? Okay, so we're going to break this one up into 3s. And when you do, you get segments that are n over 9, right? 1/3 of n over 3. So n over 9, n over 9. And then we'd add that equilateral triangle, so that's n over 9, and that's n over 9. So this segment right here becomes this, which has a full length of 4n over 9. Correct? But then we got 4 of them, 1, 2, 3, 4. So the total would be 4 times 4n over 9. 4 times 4n over 9, which is 16n over 9. And that is the length of path 2. Okay, so what it looks like to me, from going from n to 4n over 3, and then to go from 4n over 3 to 16n over 9, it looks like you're multiplying each time by 4 over 3. Is that right? Yeah. So that is the pattern that I was trying to find, because otherwise you'd have to keep doing this, manually. So that means path 3 would be 4 over 3 times this guy, which is 16n over 9, which I believe is 64n over 27. And then path 4 would be, again, 4 over 3 times this guy, 64n over 27. And that is 256n over 81. And then finally, path 5 would be 4 over 3 again times this guy, 256n over 81, which is 1024n over 243, I believe. 243? Yeah, in lowest terms, I believe. Yeah. So what they want is, what is the smallest possible value of n, since n is an integer? Okay, so this has to be an integer. So 1024n over 243 has to be an integer. Okay, can we, if n is 243, then this would cancel out. This would cancel with that. And I think, yeah, I think this is in lowest terms. Yeah, let me think about this. 1024 is what? 1024 is 2 to the power of 10. And then 243, I believe, is 3 to the power of 5. So there's no common factors here. So that means this 1024 over 243 is already in lowest terms. So n has to be 243 in order to cancel that out. And that's the smallest value of n to make this an integer. All right, that answered that question. The arithmetic mean of two positive real numbers, x and y, is half the sum of the two numbers, or x plus y divided by 2. The geometric mean of two positive real numbers, x and y, is the square root of the product of the two numbers, or the square root of x times y. What is the arithmetic and geometric means of 36 and 64? Okay, so arithmetic mean would be 36 plus 64 divided by 2, which is 50. And the geometric mean, GM, would be 36 times 64 square root, and when you do that, you get 48. Determine a pair of positive real numbers whose arithmetic mean is 13 and geometric mean is 12. So this time we'll call it a and b, and they're saying that a plus b divided by 2 is 13, and that ab, the square root of that, is 12. So that means that a plus b is 26, and if we square both sides, ab is 144. Okay, so where do we go from here? Well, there's a few ways of doing this. Let me just see what's the quickest. We can substitute one for another and you get a quadratic or whatever. Well, one thing that came to mind is a plus b squared is a squared plus b squared. So sorry, 2ab plus b squared, like that. And I can substitute this in. So 26 squared is a squared plus b squared plus 2 times 144. So if you isolate for a squared plus b squared, you get 26 squared, which is 676, minus 2 times 144, which is 288. So this gives me 388. So I've got to come up with two perfect squares that add up to 388. Okay, Well, let's make a list here. We got a plus b. We have a, b, and ab. Okay. Shouldn't be that hard, I think. Well, a plus b is always 20. Well, okay. Well, let's just start with the ab. That might be a little bit easier. So, how about 12 and 12? That would give me 24 here. So that's no good because it's got to be 26. Okay, two numbers that multiply together to get 144. How about 18 and 8? 18 times 8 is 144, right? Yeah, 72 times, yeah. And then this is 26. Okay, that works. Well, there you go. I just got it just by trial and error there. So A is 18 and B is 8. And I believe that's it. For two positive integers x and y, the arithmetic mean minus the geometric mean equals to 1. With justification, determine all such pairs where x is less than y is less than or equal to 50. Okay, so the arithmetic mean of two numbers minus the geometric mean, they're saying is equal to 1. Okay, so let's work with this one. Multiply through by 2 first of all, and then that gets rid of the fraction. And then let's put everything on, let's see, what should I do? Let's see here. Let me rearrange this a bit. 2xy plus y, because this looks like it might be able to factor, but so this is really like root x times root y plus y. Yeah, this looks like it factors, but to make it a little bit easier to understand, I'm going to make some substitutions. Root x equal a and root y equal b, and that way x would be a squared and y would be b squared. I think this would be a little bit more easier to understand than roots. So if you plug that into here, this will be a squared minus 2ab plus y is b squared. Does that look easier? Hopefully. And this factors beautifully into a minus b, all right? Is that right? A minus b squared? Yeah, okay, great. So that's nice. Okay, so where do we go from here? I guess I can take the square root. So a minus b would be plus or minus root 2. And let me just write down the conditions because we have to abide by some conditions here. X minus y minus x is less than y is less than or equal to 50. Okay. So making that substitution, what we did up here, that means that a squared is less than b squared, which is less than or equal to 50. Yeah. So that means that a has got to be less than b, I believe. Because they're positive, right? They're positive? Yeah, they're positive. Okay, that's why we can make that conclusion. Okay, so now we got that. Let's move forward here. So far, so good. And so since a is less than b, that means a minus b would be less than 0. So that means a minus b has got to be the negative guy. Yeah. Okay. And then I'm going to just switch this around to get rid of the negative. So b minus a is root 2. So that means b is equal to root 2 plus a. Okay, well, finally we got one variable in terms of the other. And then now let's switch back to our x's and y's, since that's what we are dealing with. Recall b was root y, and a was root x. So this is really what we got down to. And then we will bring this guy back, this guy right here. Where is it? This one right here. We'll bring that back. And I'll just write it in terms of y. Y is equal to 2 plus 2xy minus x, I believe, right? That would be the correct way of writing that. Okay. Or instead of using that, what we can just do is just square both sides here. I think that might be a little bit beneficial. So if I square both sides, this side you get y, and this side you'd get 2 plus 2 root x plus x. Yeah, this is going to be helpful. Okay, now recall y and x are both integers, right? The only way this can be an integer is if this whole thing is an integer. Well, that's an integer and that's an integer. So now, therefore, this guy has to be an integer. So root 2 root x has to be some integer. You got it? And the only way that's possible is if x has a root 2 in it. Like if x is equal to 2 and then some square. So for example, that means that root x would be root 2 p, and then if you put this here, root 2 times root 2p would be 2p, and making that an integer. So this is a very important conclusion here. So let's make a list of x and y and p, and let's go through this list here. Now recall, we've got this condition that x has got to be less than y has got to be less than 50. So once we get the y value of greater than 50, we will stop. So p is a prime number, and we'll start, well, p is any number actually, not necessarily a prime. So let's start with the smallest number that's positive, which is 1. If p is 1, then x would be this guy 2, and then y, we can substitute that into here, and you'll get a value of 8. If p is 2, you'll get 8 and 18. If p is 3, you'll get 18 and 32. If p is 4, you will get 32 and 50. And then after, if p is 5, this will be greater than 50. So since we have to abide by those parameters, these are the only 4 pairs that fall within those guidelines. Suppose that c is a real number. Solve the following system of equations for x and y in terms of c. We have 3x plus 4y is 10, and we have 5x plus 6y is c. We'll call this equation 1, we'll call this equation 2. And let's solve this. So 5 times 1 minus 3 times equation 2. That would give me 15x plus 20y minus 15x minus 18y, and that is equal to 50 minus 3c. Solving this, we get 2y is equal to 50 minus 3c, and therefore y is 50 minus 3c over 2. And then plug this back into any one of these guys. For example, it doesn't really matter where you plug it into, but you can plug it into this one, for example. So x, if you isolate for that, is 10 minus 4y over 3. So if you plug it in there, it's x 10 minus 4 times y, which is 50 minus 3c over 2, all over 3. And then this continues as x is equal to 10 minus 200 minus 12c all over 2, I believe. And then that's all over 3. So this becomes 20 minus 200 plus 12c. Don't make that mistake. All over 2. And that's multiplied by 1/3. So this will be x is equal to 12c minus 180 all over 6, and that finally becomes 2c minus 30. So my x is 2c minus 30, and my y is 50 minus 3c all over 2. Part B. Determine all the integers d for which the system of equations x plus 2y is 3 and 4x plus dy is 6 has a solution xy where x and y are integers. Okay. So we are given x plus 2y is 3 and 4x plus dy is 6. So we'll call this equation 1, we'll call this equation 2. So same story. Let's see what I can do here. 4 times equation 1 minus equation 2. That would give me 4x plus 8y minus 4x plus dy. And that is 12 minus 6. So this becomes 8y minus dy is 6. And therefore y would be 6 over 8 minus d. Now, I believe that is correct. Okay. All right, so what do we do now? Y is equal to 6. I guess this is a pretty important finding because then we have to figure out values of d that would make y an integer because they're integers, right? Let's just double check here. Yeah, they're integers. Okay. Well, the only way that y can be an integer is if 8 minus d is divisible into 6. So that means that 8 minus d can be either plus or minus 6, plus or minus 3, plus or minus 2, or plus or minus 1. I believe those are 8 possibilities. So this is just a bunch of time-consuming stuff. So for example, 8 minus d, if it equaled 6, that means d would be... what would be d? D would be 2, right? So if d is 2, then we plug it into here, and then we get y is equal to 6 over 6, so y is 1. And then I guess you'd plug that back into one of these guys. If y is 1, then that looks to me that x would be 1 also. So there you go. You got your first pair, xy is 1, 1. And then you just continue like that. So should I do them all? You want me to do them all? I'll just do a few more because I'm sure you're capable of doing them all. So the next one, 8 minus d is minus 6. Right? We're still dealing with this guy. If that's the case, that means d is 14. If d is 14, then you sub it into here. Then you get y is equal to 6 over 8 minus 14, which is minus 6, right? Yeah. So that means y is minus 1. And then if you substitute that into here, you get x equal to 5. Yeah, so then you got another pair. Negative 1. Oh, sorry, 5, negative 1. And then you just keep going. So I'll just give you the d values. You guys can do this. It's fairly simple algebra. So the d values, the first one, 2, then 14, the ones I just solved. You're also going to get a 5, an 11, a 6, a 10, a 7, and a 9. The corresponding values for y, well, the first two I just solved, 1 and negative 1, I believe. But then you're also going to get a 2, a negative 2, a 3, a negative 3, a 6, and a negative 6. And then the corresponding values for x would be 1, 5, which I just showed. But then you're also going to get negative 1, 7, negative 3, 9, negative 9, and 15. And then, of course, you just write them out like I did in terms of ordered pairs. And finally, determine a positive integer k for which there are exactly 8 integers n for which the system of equations has a solution where x and y are integers. All right. So let me just see what they're talking about. For a k, some value of k, there's going to be 8, exactly 8 n that give you integer solutions. Okay. So, kind of a Not a very straightforward question, but let's just see what we can do. Well, they're giving us these equations, so let's call this 1, and let's call this 2, and let's see what I can do to solve them. What can I do to solve them? Let me see here. If I multiply the first guy by -2 and the second equation by 3, they might be able to match up in terms of helping me. So then this one would give me minus 18n plus 12x plus 6n plus 4y is equal to minus 6n squared minus 12n minus 6k plus 10. Correct? All right, and then the next one, if I multiply by 3, that should be pretty straightforward. 18n plus 12x. So yeah, it did match up really well. 9n squared plus 6n y minus 3n squared plus 6k plus 6. Okay, good. So now let's add these guys. And when you do, a bunch of stuff cancels out. So let's see here. What do I get? 9n squared plus 12n plus 4, and that's still in brackets in front of y. Now on this side we get minus 9n squared minus 12n minus 4. So that means that y looks to me like it's -1. Yeah. Okay, that's very nice. So we got that. So I guess we just go back and substitute that into any of these. So I'll just substitute it into 1. And if I substitute that into 1, I'll get 9n plus 6x plus 3n plus 2 is equal to 3n squared plus 6n plus 3k plus 5. Okay. All right. What do I do here? I guess just the only thing I can do is collect like terms. It's not much else. Put everything on one side, and we get 3n squared plus 3n plus 3k plus 3. Correct? And I think that's about as far as I can go there. And then I will again substitute that y equals -1 to the second guy. And when I do that, I get 6n plus 4x minus 3n squared plus 2n is equal to minus n squared plus 2k plus 2. And if I isolate this guy, I will just have on this side a 2n squared plus 2n plus 2k plus 2. All right, that's about as far as I can go. So I'll call this equation equation 3 and equation 4. And then I've got to figure out a way of solving these since I have less variables. All right, so how about, let's see here. Well, this looks very similar to this right here. So if I divide the equation 3 by 3, then that would be 3n plus 2x is equal to n squared plus n plus k plus 1. And if I divide equation 4 by 2, that's going to be 3n plus 2x is equal to, let's see here, n squared plus n plus k plus 1. Same thing. Okay, well, that doesn't help, but in a way it helps, but I guess it just helps to isolate the x, n squared, since they're getting the same thing all over 3n plus 2. Okay. All right, so I got it down to here. And recall, x is an integer. X is an integer. Okay. All right, so now what? Where do we go from here? I guess we have to play around with this. We got to do some fancy algebra now. We got to do something called fancy algebra, which is not always obvious, but it's basically the result of many months or even years of practice. Okay, so let's see what we can do. If I multiply by 3, I'm going to get this 3n squared plus n plus k, all that stuff, right? And the goal is to kind of get an integer out of this. Now let's see if I can do that. So this will be 3n squared plus 3n plus 3k plus 3 all over 3n plus 2. And then this guy, if I break this up, 3n squared plus 2n plus n plus 3k plus 3. So just broke up this guy into these two. I'm trying to see if I can factor anything. And then this will, if I factor out an n here, I get 3n plus 2. And then on this guy, I get a n plus 3k plus 3. And that's over 3n plus 2. Okay, I'm getting somewhere. Not really getting a lot, though. This just boils down to this. 3k plus 3 all over 3n plus 2. And that was x, right? Yeah. Okay, so what have I achieved by doing that? Oh, sorry, I think this was 3x. Yeah, sorry, 3x, because it's 3x up here. Okay, so let's discuss this. What have we achieved here? Well, is n an integer also? Let me go back to the question. Integers n, yeah, n is an integer. So x is an integer and n is an integer. So this is an integer. So the only way that 3x could be an integer is if this is an integer. So we have to now concentrate on making n plus 3k plus 3 over 3n plus 2 an integer. And I think we got to go through the same process here. Let's call this m, some integer. And then again, let's multiply it by 3. And let's see if we can break this up into some integer plus some fraction. So this becomes 3n plus, let's just leave it in brackets for now. N plus 3k plus 3 all over 3n plus 2. And then now let's expand. So 3n plus 9k plus 9 is 3n plus 2. And then we got 3n plus, let's break this up into 2 and 7. And then this, now therefore this guy would combine with this guy to give 1, and then it would just be left with 7 plus 9k over 3n plus 2. And that's 3m. Okay, so this is an integer, that's an integer, so this must be an integer. So that means 7 plus 9k over 3n plus 2 must be an integer. Okay, so that is finally what we've got to do. That is our final step. So our goal is to make this an integer. Okay, so how do we do that? Well, we got to do trial and error. We got to make k, we got to do n, and let's see what we get. Okay, what did they give us for parameters for k? Did they tell us anything about k? It's just a positive integer. Okay, all right, well, that's pretty easy. I mean, not easy, but that helps. That helps, gives us a good framework. Okay, so we are trying to make this guy an integer. Okay, let's start with k equals 1. If k equals 1, then n, oh, we got to figure this out. Oh boy, I got it. I understand now. Okay, so k is equal to 1. So this is just one of those really time-consuming questions. If k is 1, 7 plus 9 over 3n plus 2. So we get 16 over 3n plus 2. Okay. So that means 3n plus 2 has to divide into 16. So it's got to be either plus or minus 16, plus or minus 8, plus or minus 4, plus or minus 2, or plus or minus 1. And solving, when you solve for this, I'll let you guys solve it. You get 5 solutions. Yeah. So I'll just put that there are 5 solutions. Yeah. Now, we wanted 8, right? Yeah. So this fails. Even though they're solutions, we want exactly 8. So one of these k's, I don't know which one it is, for some value of k, ... you're going to have exactly 8 solutions for n. Want 8 solutions. that meaning 8 values of n that are integers. Now, I just want to 7 plus 9k over 3n plus 2. I'll just put that in there. I just want to point out that there's a kind of a quick way of solving for these. You just want to look for numbers that, a quick way of solving these guys. Look for numbers that are 2 more than a multiple of 3. So that's what this is, right? It's 2 more than a multiple of 3. So 2 more than a multiple of 3, for example, would be 8. So that's why you can quickly get an integer solution, whereas some of the others are not 2 more than multiple of 3. Instead of have to manually do all these, you can kind of quickly do it in your head if you look at that. Okay, so similarly for k equals 2, k equals 3, you do the exact same thing. So if k equals 2, plug it in there. So we get 7 plus 18, so 25. So it'd be 25 over 3n plus 2. And same thing. So 3n plus 2 is going to be either plus or minus 25 or plus or minus 5. And then you have to solve for n and see how many values of n are integers. And when you do, you obviously, for that one, oh, plus or minus 1, sorry. Plus or minus 1. So that gives you less than 6. Because even if all of those 6 gave you integers, you'd have at most 6. So you just keep on doing this. K equals 3, k equals 4, k equals 5, k equals 6, and so on. And I'll just do it for you really quickly. If k equals 3, then the 7 plus 9k over 3n plus 2, that guy. Well, if k equals 1, it was 16 over 3n plus 2. If k equaled 2, it was 25 over 3n plus 2, right? If k equals 3, it's 34 over 3n plus 2, and therefore, I'll just do it here if I can squeeze it in. If k equals 3, then that means that 3n plus 2 has to be equal to plus or minus 34, or plus or minus 17, or plus or minus 1. So again, this is going to give you at most 6 solutions. You see what's happening here? So it's just really time consuming. The algebra is fairly straightforward. And then I'll just fill it in. This will give you less than or equal to 4 solutions. This one is this guy. When k equals 5, you'll get 6 solutions. When k equals 6, you get less than or equal to 4 solutions. When k equals 7, you finally get the full 8 solutions. And I'll let you guys do the algebra. It's fairly straightforward. But I'll just fill it in. When k equals 7, you basically have a 70 over 3n plus 2 scenario. And therefore, 3n plus 2 has to be equal to plus or minus 70, plus or minus 35, and plus or minus 14, plus or minus 10, plus or minus 7, plus or minus 5, plus or minus 2, and plus or minus negative 1. And of these, when you solve for n, you'll get 8 values of n that are integers, and therefore you have 8 solutions. So that is the value that they are looking for, and that completes the question.